Okay, the next one we're going to build is the turbine. So we'll write out our basic equations for the turbine. Here I'm going to make some assumptions. No change in kinetic, no change in potential, no heat transfer, and one inlet and one exit. So I have, for those conditions, the work for the turbine equals m dot times h inlet minus h exit. And maybe the temperature at the inlet and the pressure at the inlet are specified, and the mass flow rate. And from those, I can get the enthalpy, and then most likely the pressure at the exit is going to be specified, and we'll be given a turbine efficiency. So the turbine efficiency is defined as the ideal over the actual work. So the ideal is HI minus HES, and the actual is HI minus HE. So that gives me that the exit enthalpy equals the inlet enthalpy minus the turbine efficiency times HI minus HES. So I can put this in here. And then the HES is found, then HES is a function of P exit and S inlet. So we're making the assumption that the exit entropy is equal to the inlet entropy. And then, so that's why there's an S here, so the entropy doesn't change. And then after I put that into this formula, I get the actual enthalpy. All right, so let's try and build this. So I've got here the state across the turbine changes. So I specify now we're going from left to right. So it equals whatever this state is plus 1. That way it will number my states for me. So I have the pressure given here. And I guess the first thing I want to try and find is the enthalpy. So I'm going to use this function. So I'm going to write equals enthalpy at the inlet. So actually maybe I should work on getting a value for that first. So this is equal to water. And I know the temperature and the pressure. So temperature, pressure. I want enthalpy in quotes. And then specify where the pressure temperature is first, and the second variable is pressure. Right, now I can come over here and specify, but I'll need a SI, so let's do that while we're at it. Equals water TP, and this time I want entropy, and specify temperature and pressure. And then, as I showed you in the last problem, use a function that I defined called x, and I specify the pressure and the enthalpy, and it will give me quality. And if I get a value greater than 1, it just means it's superheated. It's not really defined. Quality is not defined above 1, but this means it's far away from being saturated, so it's superheated. All right, now I can write this function. So over here, I'm going to use this equation. So equals enthalpy at the inlet plus the efficiency, and the efficiency is right here, times H inlet, which is this inlet, minus HES. So I'm going to use water, and I'm going to specify pressure and entropy. So PS is the order that those are given. And I want enthalpy, doesn't matter which case, and I specify where the pressure is, so it's this exit pressure, but it's equal to the inlet entropy, so that's my HES. And then I end the quotes for the term here that I'm multiplying by, and I get 3946.93. Now that's different than what I have here, so something, okay, so I have plus, and I should have put a minus. There we go, 3432.43. And now I can get my values from those two values. So let's start up here, equals water, temperature, pressure given, and I want temperature. And let's actually change that because I'm trying to find temperature. So we want pressure and enthalpy given. And then the pressure is given here, and the new enthalpy I just found here. And that matches. And the same thing again. Equals water, pressure, enthalpy, and this time I want entropy. Pressure given, enthalpy given, and equals X, and pressure, comma, enthalpy. So it's actually still superheated. Often depends on the pressure. If I drop this pressure lower, it should go to a saturated liquid vapor mixture. Let's try 100 kPa, and it's still not quite low enough. Let's try 10 kPa, and now I have a quality of 94%. But at 1,000, it's still superheated. Okay, and then I need the mass flow rates. So I'm going to get the mass flow rates from this cell. So it should be yellow. Hopefully it is in the one I send to you. So this is a constant, so it equals 90. And then at the exit, it's the same mass flow rate. And that looks like it matches. Now we're missing the work. So the work for the turbine equals mass flow rate times H inlet minus H exit. And so that matches. Now if it wasn't a perfect turbine, then you should get these values if you typed everything right. So for a 90% efficient turbine, you'll get less work out, and you'll get different entropy, enthalpy, and temperature. So even quality will change. So that's one way to just make sure you typed in everything right. And that matches the values here.